Hi everyone, my name is Joris Guérin and this is our 4-minute presentation for our ICRA paper, Evaluation of Runtime Monitoring for UAV Emergency Landing. This is joint work with Kevin Delmas and Jérémy Guillouchet, which was conducted in Toulouse, France. This work is about runtime monitoring of deep learning perception functions, which basically means that we have a safety-critical autonomous system that's using machine learning-based functions such as neural network to process complex sensor signals, such as images, to estimate the state of the system and its environment. In such critical systems, neural networks cannot be trusted for several reasons, but a solution to that is to implement safety monitors around these networks to ensure that we can detect its errors and handle them. To study this important problem, we decided to go through a use case of UAV emergency landing. So it's basically a drone in a city that's taking images and needs to select an area where it would be safe to land. So we build this full architecture, which uses semantic segmentation and then process the segmented image to select a landing zone that would be safe for the drone to go. In addition to that, we built several runtime monitoring mechanisms to either accept or reject these zones, and we studied them through our example. So the three monitors that we implemented is, the first one is called local high definition, which is basically increasing the definition of the image locally around the landing zone that we selected and reprocess the image to get a better estimate of the categories that are in it. The second one is called classification hierarchy, and it's basically a smart way to handle uncertainty about the classes. And finally, Monte Carlo dropout is a better way to estimate this uncertainty. To study the influence of these monitors, we built a complete evaluation data set composed of several images, perturbed images with realistic perturbation corresponding to either external conditions, errors due to drone motions, or sensor faults. And we evaluated our monitors against different metrics, so either individual binary classification metrics, so for example, precision, recall, or false positive rate, and we compare them to custom system-level safety metric that we implemented, which is called safety gain, which basically compares the risk with the monitor against the risk without the monitor. So the main results we got from these experiments is first that for UAV emergency landing, a good runtime monitor must have a low false positive rate, as we can see here, which is the most important parameter. So here, basically conservativeness, which is usually a desirable safety property, is not good. Too much conservativeness is not good. The second main result is that the only really impactful monitor that we had was the local high definition one. As we can see here, local high definition had a significant impact, but combining with the others tend to decrease the safety of the system, which suggests that we should probably focus on the information we provide to the monitor rather than the monitor itself. And finally, the last one is binary classification metrics can be relatively good for some of the monitors, but safety gain can also be almost zero even for these good binary classification monitors, which means that standard binary classification metrics are not very well suited for evaluation of safety impact of monitors. So there is a need for unified evaluation metrics for runtime monitoring in future work. That's it for this short presentation. If you want more details, feel free to contact me either directly now through questions or through any of these mediums. Thank you.